Hi there. So we're going to talk about enthalpy and specifically how energy flows relate to changes of state. So first, let's just review the three most common states of matter: solids, liquids, and gases, and remind ourselves as to what the transitions are among each of these three states. So if you're going to convert solid to liquid, you realize that that requires adding heat, and so that's a red line, and that's what we call melting. But to go the other way, to go from liquid back to solid, that's a cooling process, and that's what we call freezing, and you guys know that. Now, to go from liquid to gas, again, takes an input of energy, and that's vaporization. And when we get up to the boiling point of a liquid, that's we call that the boiling point. And at that point, vaporization is happening, fairly rapidly. And the converse, if you want to go from a gas down to a liquid, that's condensation. Now, the transitions between solid and gas, where we don't pass go, we skip liquids altogether and go straight to gas. That these transitions back and forth are probably a little more obscure, and you might not remember those. So to go directly from solid to gas, that's sublimation. Carbon dioxide is a substance that is known to sublime. You don't find any liquid carbon dioxide at atmospheric pressure and normal temperatures. And then probably the most obscure phase transition of the six is what we call deposition. So when a gas converts directly to a solid, that it's said to deposit on the solid, and so that's called deposition. And just to be clear about the color scheme, as I said, whenever you see red, that's a transition that requires energy to be put in to the system. It takes work to do that, and so that is an endothermic process. And the value of the heat flow would be positive with respect to the object. Conversely, the transitions like freezing, if you put a tray of water in your ice cube tray, if you put that in the freezer, what your freezer is doing is removing the heat energy from the water to convert it to a solid ice, and so that's a negative energy heat flow, and that's exothermic. Okay, so that's phase transitions. Okay, now what we specifically want to talk about in this video are we're going to get to a couple of processes called heat of fusion and heat of vaporization, and those are, I think, most easily understood in the context of a heating curve. So what I've got here is I just have temperature going on the vertical axis, and then heat energy on the on the x. So as we go from left to right on the horizontal axis, we are adding heat energy to some object. On the left right now, I'm being a little cagey about the temperature value of the boiling or the melting point and the boiling point, and that's because I just want to keep this general for any substance. We're going to be talking about water, but you should know that this could be any melting point and boiling point, and so that's what these dashed reference lines are for, just to kind of remind us that when we cross one of these boundaries, we are making a phase transition, either from solid to liquid or liquid to gas. Okay, so let's say we are talking about water. All right, so then of course the melting point is 0 degrees Celsius, the boiling point is 100 degrees Celsius. And let's say we have a little block of solid water, okay, otherwise known as ice. And let's say that this block of water, block of ice, is at 25 degrees below 0 Celsius. So it's, really, really frozen. It's very cold. So on our heating curve, we would be right here. Okay, so we have not added any heat energy yet, and we're about right here on the temperature scale. Okay, so we're well into the solid phase. But let's say our objective is to get to here. Okay, we want to be at 0 degrees. We obviously, at this point, we will have added some heat energy, and what we want to see at the end of the heating process is we want to convert this block of ice into a puddle of water. Okay, so we want to have it completely converted to liquid, but we want it to be at 0 degrees Celsius. Okay, so the question is, how much energy would it take to get there? Okay, it's a very, it seems like a very kind of elementary, primitive question, but it actually begins to open up some kind of deep, interesting concepts that we need to learn about. And this is where the heat of fusion comes in. Okay, so let's begin our journey. So the first thing we do is we start to heat it, right? We put it on a hot plate. We put it on the stove, put it over a Bunsen burner, whatever. But we're adding heat energy, and as we do that, the temperature is going to start to rise. Now, because it's 25 degrees below zero to start, as we add energy initially, it's not going to melt. Okay, so that's one thing that's maybe a little bit counterintuitive. It's easy to think, well, if I have ice and I heat it, it's going to start to melt. Well, not until you get the temperature up to the melting point. Okay, and then when you get to 0 degrees Celsius, the next microjoule of heat that's absorbed will then go into melting it. Okay, but interestingly, the temperature will not change. Okay, so here's what we're trying to do. We're trying to, in step one, we're trying to heat the ice from -25 to 0 degrees Celsius. Okay, so now that we're at 0 degrees Celsius, okay, got ahead of myself. So now we're in a position to calculate how much heat did it take to get from here to here. And that's just a simple MC delta T problem. So here we're assuming that we have, let's say, 36.04 grams of ice. And here's something that's interesting. You probably were expecting 4.18 joules per gram Celsius, like it is for liquid water. But for when water is in the solid phase, it has a lower specific heat. It takes less energy per gram of ice to raise the temperature, about half as much. So anyway, I just want you to get used to the fact that specific heat values are specific, no pun intended, to the state of matter that they're in. Okay, so we got the specific heat, and then obviously if we're going from -25 up to 0, that's a 25 degree change in temperature. And when you crank through that, you'll get 1847 joules. Okay, so now we know how much energy it took to get from here to here. Now, next phase. As we continue heating, notice, interesting, the temperature doesn't budge. We've flatlined. We're going to be on a temperature plateau here until we melt the last little bit of ice. Okay, so right now what we're doing is we're melting the ice, and it's starting to turn into a liquid. So I want you to remember that as we're on this heating plateau, or this temperature plateau, we have two states of matter that are in contact, that exist at the same time, solid and liquid. All right, and the whole time the temperature doesn't budge. It stays right at 0 degrees Celsius. Did I mention that? So finally, we get to our objective, and now we need to calculate how much heat energy did it take to get from here to here. Okay, during the melting stage. And yeah, at that point we'll have all completely liquid. Well, to answer this question, how much heat would it take to get from here when we first reach 0 degrees and to melt all of that ice? Well, we got to look a little bit more deeply at the melting process. So let's say this illustration is just to I'm trying to represent water molecules. Okay, I'm representing them as circles, and they're in a rigid lattice orientation because they're in the solid phase. And what we're trying to do is we're trying to affect a phase transition between solid and liquid water. And so obviously to do that, we're adding heat, like we said. And as we add heat, what we're doing is we're breaking the hydrogen bonds that hold the water molecules in their lattice positions. And all of this heat that's being absorbed during the melting process, it's not raising the temperature. That is, it's not increasing the average kinetic energy of the molecules. It's simply breaking the connections among the water molecules, and it's allowing them to behave like a liquid. That is, they're kind of gliding past each other, and that takes a lot of energy. In fact, this is where the heat of fusion comes in. So the enthalpy of fusion is the heat that's required to melt 1 mole of a substance at its melting temperature. And for water, it takes about 6 kilojoules of energy per mole. Okay, so here's the definition. So that's a definition that we need to know. Okay, so let's get back to our heating curve. So now we're in a position to calculate how much heat it took to get from right here to right here. And so the way we'd set this up is, we know we have 36.04 grams. We have to convert that to moles first, so that we can then use this conversion factor, 6.01 kilojoules per mole. And when you do that, you'll calculate that it takes 12.02 kilojoules. All right. Okay. So now we're in a position to calculate the total energy that it took to get from minus 25 up to 0 degrees and completely melting the ice. And all we do is we simply add these two components. Now notice what I did here. I had to convert this from joules to kilojoules so that my units are consistent. So I rounded this to 2 decimal places in kilojoules, and you should come up with 13.87 kilojoules. Okay, so now we know how much energy it would take to convert 2 moles of water from here to here. All right, so let's move on. Let's say we want to keep going, and we want to continue to heat that water, which is now at 0 degrees, all the way to the boiling point. And furthermore, we want to be able to convert that all the way to steam. Okay, so now to go from here to here, hopefully you realize that this segment of the heating process is just another specific heat problem. Okay, so we know how much mass we have, 36.04 grams. Now we need the specific heat of liquid water, which is 4.18 joules per gram Celsius. And obviously, we're going to increase the temperature by 100 degrees. So our delta T is 100 degrees. So once you go ahead, work that through on your calculator and see what you get. Hopefully you came up with 15,060 joules, which when you convert to kilojoules turns out to be 15.06 kilojoules. Okay, so that's how much energy it took to get from here, right here, to right about here. Okay, so we're right about there on the energy scale. Now, to get from here to here, we're simply boiling. Okay, so right now at this point, we have liquid water, and it's at 100 degrees. And now it's going to start boiling vigorously as we go across and continue to heat. Now notice that as we're heating during this phase transition, the temperature again flatlines, and it stays at 100 degrees. Okay, so now how much energy does this take to get from here to here? Well, that is what we call the heat of vaporization, or the enthalpy of vaporization. So let's say here's our beaker of water, and the water is, obviously it's a liquid when it's boiling, and we're trying to affect a change of state from liquid to gas. So we're adding a lot of heat to try to get it to boil, and when it's boiling, this is what's happening. We are taking molecules from the liquid phase, and they're breaking free of the intermolecular interactions, and they're going up into the gas phase where they're absolutely, alone. And that takes a lot of energy. It takes a lot more energy than it does just to melt something generally. So here we go. Here's the enthalpy of vaporization. That's the official term. And for 1 mole of water, if you want to convert 1 mole of liquid water to a mole of water in the gas phase, at 100 degrees Celsius. It takes 40.7 kilojoules. And notice the heat of fusion was like 6 kilojoules per mole. This is almost 7 times more. So it takes a lot more energy to do this than it does just to melt something. Okay, so here is a definition for the molar enthalpy of vaporization. Okay, so back to the heating curve. So how much energy would it take? Excuse me. So if you set it up, you've got mass. Here is the mole to mass conversion. And once you're in moles, and I think you can see that 36.04 is exactly twice 18.02, the molar mass of water. So we have exactly 2 moles of water. And so if it takes 40.7 kilojoules for 1 mole, then you know it's going to take twice that much for 2 moles. And so that's 81.4 kilojoules. Okay, so now let's add up the energies that we calculated. So we have, this is the 3rd component and this is the 4th component, and so the heat for components 3 and 4 is simply the sum of the two, which is 96.46 kilojoules. Alright, and then finally, to kind of bring it all, to add everything up, how much energy did it take to get from minus 25 degrees in the solid phase all the way to the gas phase at 100 degrees? We simply add the, make the grand total, and that comes to 110.33 kilojoules. All right, so this is exactly the kind of thing that we're going to need to be able to do on our problem sets and quizzes, and I hope that this helps. Just to kind of summarize now, notice that when you are looking at a heating curve, this segment here that goes along the melting point, the solid-liquid boundary, this is a phase transition. The substance is going to be both solid and liquid simultaneously because you're melting, or freezing if you're removing heat, and the quantity that you'll need to use is the molar enthalpy of fusion. And then up here, this phase transition that goes along the liquid-gas boundary, this is obviously when vaporization or condensation is happening, and you have 2 phases that exist at the same time, liquid and gas. And the value that you need to use for calculations along here is the molar enthalpy of vaporization. Okay, so finally, I just wanted to have you work 2 quick problems before we go, just to make sure that you know exactly what's going on. So let me ask you to try and work this problem. Okay, so this is a molar enthalpy of fusion problem. So how many kilojoules of heat would you need to melt a 50-gram block of ice? So here you're simply going along the phase transition where you're converting solid to liquid, and so the amount of heat that's required. Hang on one second. Let me check my time here. Okay, 50 grams, and you got to get that into moles. So 1 mole over 18.02 grams, and then you multiply by the molar heat of fusion. 1 mole. Okay, so notice I'm taking mass, the mass that I was given, sorry about that, divide by the molar mass to get it in moles, and then you can use this conversion factor between 6.0 kilojoules and 1 mole. And when you do that, you should get 16.7 kilojoules. Okay? Now, how about this one? So try this one first on your own. Okay. So here, it's the very same setup. So we take this time 63.7 grams and convert that to moles. So you divide by the molar mass, which is 18.02. And this time, we're going to multiply by the molar heat of vaporization, which is 40.7. Okay? And when you do do the calculation and round to whole numbers, you'll find that comes out to 144 kilojoules. Okay, so I hope that this helps kind of get your mind around heating curves, heat of fusion, and heat of vaporization.